Hi, this lesson is about continuity, the different types of discontinuities, and the intermediate value theorem. So we start with continuity. So here's our definition. A function f is continuous at a number a if the limit as x approaches a of f of x equals f of a. So the limit must exist, the function must exist at a, and they must be equal. So if you're ever asked to prove if something is continuous, you'll be using this definition right here. And theoretically, what that means is a continuous function has the property that a small change in x produces only a relatively small change in f of x. So if you're close to a with respect to x, values that are close to f of x should also be close to f of a when you are close to a. So just to spell it out more clearly, f of x is continuous at a if f of a is defined, meaning a has to be in the domain of f. The limit of f of x as x approaches a exists. And remember what that means. It means that both your left and right hand limit must be equal from the left and right of a. And the f of a value and the limit value must be the same. So let's talk about different types of continuity. You could have a function that is continuous at a, or you could have a function that is continuous from the right or continuous from the left, but not continuous overall. So if the limit as x approaches a from the right of f of x equals f of a, then we consider that to be continuous from the right. F is continuous from the right at a. And the opposite is true. If the left-hand limit of f of x equals the same value as f of a, then you would say that the function is continuous from the left. So a picture of what that would look like is here in purple. This is a graph of f of x, looks like a piecewise function. And in this case, this graph is continuous from the right at -2, but it's continuous from the left at 1. And that's because the limit as x approaches -2 from the right is equal to the same value of f of -2, which is this value here, which is 3. But then at 1, the limit as x approaches 1 from the left, and so as you get closer and closer to 1 from the left, the function is approaching this value here, which is f of 1, which has a value of -3. Okay, so let's talk more about continuity and figuring out if something is continuous. So we want to determine if f of x equal to 2x cubed minus 3x is continuous at -2. All right, well, this is definitely going to be continuous at -2. We're going to prove it by using our definition, but f of x is a polynomial function. Polynomial functions are functions where your exponents are whole numbers. And so in these cases, your domain is all real numbers. So -2 is an element of the real numbers, so it'll work. All right, so let's show that it's true. We know that -2 is in the domain. You can figure out what f of -2 is by just substituting that in, which is what I did here. So f of -2 is -10. But you can also compute the limit. And because -2 is in the domain, you can do that by direct substitution. So you get the same value here and there. And so therefore, your function is continuous at -2. All right, so now let's look at this piecewise function. I've given you a piecewise function. It's a line for values of x greater than or equal to 2. It is a quadratic for values of x less than 2. So the x plus 1 part is here. That's the line for values of x greater than or equal to 2. And the parabola part is here. And notice that at 2, their values, when you plug in 2 here, that'll be 3. But when you plug in 2 here, even though that would be an open circle, it's also 3. So therefore, at 2, 3, you should see a closed point there because the first one is closed. So when we're trying to figure out if it is continuous at 2, we need to show that what the left and right hand limits are in order to determine what the limit is, and then evaluate the function. And if they're the same, then we can conclude that it is continuous. So the right hand limit is right here, that we're looking at this part of the graph. Values of x greater than or equal to 2 mean you substitute that by direct substitution into x plus 1, and you get a value of 3. On the left side, you're looking at the parabola. So again, when you substitute that in, we get 3. So the limit is 3. And f of 2, when you plug in f of 2, well, this is equal to 2 here. So then you plug it into the line. So you also get 3. So the limit is 3, the function is 3. Therefore, you can conclude that the function is continuous at 2. An easy way to determine continuity from a graph is to visually see if you can draw the graph without picking up your pencil or pen or marker, then it is continuous. So you could see, although I graphed this in pieces because it's a piecewise function, if I had to, I could actually draw this without picking up my pen. So anything that you would have to pick up a pen is not considered to be continuous all throughout, like this example here. This example is not continuous over all real numbers because I definitely have a break at -2 and at 1. And so that's why we were only limited in our continuity. It was right continuous at -2 and only left continuous at 1. So we'll talk more about those scenarios. Those are called discontinuities. We'll get to that soon. So here, a function could be continuous over all real numbers, but it could also just be continuous over an interval of values of x. Depending on what the domain is and what type of function you're dealing with, you could have either all real numbers or just continuous over an interval of values. All right, so here's another example where we want to determine continuity. We want to determine if g of x is left continuous, right continuous, or neither at 0 for this piecewise function. So the top half is a radical function, and that's when x is less than 0. And the second half is another quadratic, and that's for values of x greater than or equal to 0. So the top half would be what I would evaluate the left-hand limit at, right? Less than 0 means it's a left-hand limit as x approaches 0 of g of x. And so that means that you can just substitute, you can put in, by direct substitution, plug in the 0. That gives you square root of 4. So your left-hand limit at 0 is 2. Then we have to look at the right-hand limit. For the right-hand limit, that's where values of x is greater than 0. And so you plug it into the parabola. And again, by direct substitution, here you get a value of -2. So your limit does not exist. And if the limit doesn't exist, you're definitely not going to have something that is continuous because the limit has to exist. But we are going to determine left or right continuity. So where is g of 0 defined? G of 0 is defined here. So if you plug it in, you get -2. Since the right-hand limit and the function value are equal, you would say that the graph is right continuous at 0. All right, so here's another graph to help us understand this right and left continuity better. So I have this graph here of f of x, and we can see that we have breaks at x equal to 0 and at x equal to 2, but we're going to figure out, is it left or right continuous at these points. So f of x is right continuous at 0, and that's because the limit as x approaches 0 from the right is -2, but so is f of 0. Notice that there's a solid point here, and that's connected to the right side of the graph. So that will always be consistent with left and right continuity. The side where the point is connected to the graph, where the solid point is, that's going to be either your right or left continuity. And similarly here, at 2, it is left continuous because that solid point is connected to the left side over here. On the right side of the graph, you have an open circle. So it is right continuous at 0, left continuous at 2. It is possible for it to be neither right or left continuous. For example, if I had an open circle here at 2 and an open circle here, that means that f of 2 would not be defined at all. And so therefore it would just be discontinuous at 2. You wouldn't have right or left continuity at 2. But that's only if both circles were open. All right, so I've mentioned the word discontinuity a few times. We're getting to that soon. So here's a theorem. So if f of x and g of x are continuous at a and c is a constant, then the following are also true. The sum and the difference of two continuous functions are also continuous. A constant times a continuous function is also continuous. The product of two continuous functions is also continuous. And the quotient is also continuous as long as the denominator is not 0 when at a. So otherwise it would be undefined. And so in something that's undefined would not be continuous because there is no point associated with that value. And this is also true. This has to do with composite functions. If the limit of if f of x is continuous at b, meaning the limit exists and the function exists at b, then the limit as x approaches a of g of x is b, then the limit as x approaches a of f of g of x is equal to f of b, right? Which makes sense. You can take the limit of this, that gives you a value of b, and then since f is defined at b, the actual value would be f of b. All right, so as promised, let's talk about discontinuities. So a function that is not continuous at a is considered to be discontinuous at a, or you would say f has a discontinuity at a. There are three types of discontinuities. The first one is called a removable discontinuity, and that exists when the limit exists, but the function value does not exist, but the limit value and the function value are not equal. So, and it is possible for the function to not exist there as well. So basically, when a graph of this would look like a graph with a hole. So this would be not equal, or f of a does not exist, just to make that a little clearer. So something like that would look like the picture here on the right. That's the graph of this rational function, x minus 1 over x squared minus a half. So if you were to evaluate that limit, you would have to factor the denominator and then apply direct substitution. You would get a half, but f of 1 is undefined because if you plug in 1 in here, you'll be dividing by 0. So the graph of a removable discontinuity looks like a graph with a hole in it. So like here, it's undefined at 1, 1/2. So it actually looks like a point was popped out of it or removed. Another type of discontinuity is called a jump discontinuity. And a jump discontinuity exists when the limit from the right exists, the limit from the left exists, but they are not equal. So they converge to two different numbers, which means they don't connect. So something like that would be the graph that you see here on the right, and that's the graph of this piecewise function. So we want to evaluate the limit as x approaches 3 of f of x, where f of x is equal to 5 for values of x greater than or equal to 3. So that's this part of the graph. It's a constant horizontal line. And the second part of the graph is negative 2x, and that's for values of x less than 3. So that's this part of the graph. It's a line going downward from left to right. And at 3, you want an open circle here because it's not, it's just less than 3. So at 3 itself, it's equal to 5, which is that point there. So you can't have two solid points above each other. That would fail the vertical line test and it wouldn't be a function. So you can see that the limit from the right is equal to 5. The limit from the left is -6. Those two limit values are different, and therefore it is a jump discontinuity. You're going to identify a jump graphically by seeing if there's one piece of a graph that then jumps to another part of the graph. So they are completely disconnected, versus a removable that everything is connected except for that one hole. And then our last type of discontinuity is called an infinite discontinuity. And that's when you approach the limit as x approaches a, either from the right or the left, and that limit goes to either plus or minus infinity. When that's the case, you're going to have something that we call an asymptote in your graph. And so here are 3 examples to show you what that would look like. So here I have the limit as x approaches pi over 2 to the left of tangent of x. So if I'm on the left side of pi over 2, that's this side right here, you can see that tangent is approaching infinity. So there is an infinite discontinuity at pi over 2. The same is true at negative pi over 2. Here it's going to negative infinity. So you actually have infinitely many discontinuities for tangent, every pi units to the left and right of pi over 2. Then I have this example here, 1 over x. That's called our reciprocal function, and that graph is right here. So as you approach 0, which is where the graph is undefined, as you approach 0 from the right of 1 over x, that graph is approaching infinity. But when you approach 0 from the left, that graph is approaching negative infinity. So we have a discontinuity at 0. And then the last example is ln of x, which is here. The domain for ln of x is only positive numbers, so you can only look at approaching the limit of 0 from the right. There's a discontinuity at 0. It's not defined at 0. And this time, as you get closer and closer to 0 on the right, it approaches negative infinity. Okay, so you often have discontinuities with rational functions, and all of your trig functions have discontinuities except for sine and cosine. Those sine and cosine have a domain of all real numbers. All right, so we're going to use some of what we just talked about to sketch the graph of a function that satisfies the following conditions. So you need to create a graph that satisfies this. The limit as x approaches -1 of f of x is 2. F of -1 is undefined. The limit as x approaches 2 from the left of f of x is -3. The limit as x approaches 2 from the right is equal to 1, and f of 2 is 1. All right, so let's see. I have a picture here. Let's see if it satisfies everything. So the limit as x approaches -1 is equal to 2. Well, that looks like it's represented here. I'm on the left side of -1. It's going closer to 2. On the right side of -1, I'm getting closer to 2. So the limit is approaching 2, but f of -1 is undefined. Oops, sorry about that. Erased the wrong thing. Let me get back that little piece here. All right, I'll just redraw it. So this is continuous all throughout here, and my graph looks like this, okay? And then the limit as x approaches 2 from the left, well, that's approaching -3, so that's that open circle that you see here. The limit as x approaches 2 from the right, that's approaching 1, so that's that closed circle. And the reason why it's closed is because you're told that f of 2 is equal to 1. So that satisfies the conditions. So let's talk a little bit more about this graph just to reinforce some of the things we talked about. So a graph like this has a removable discontinuity at -1 because we have a hole here. So we have a removable discontinuity at x equal to -1, and we have a jump discontinuity at x equal to 2, because you can see that the graph jumps from one part to another. It is right continuous at x equal to 2, because the limit on the right and the function value are the same. And it is neither right nor left continuous at x equal to -1, because it's undefined. So that's that open circle here. All right, so let's move on. This next part is is about the intermediate value theorem. So I'm abbreviating it as IVT a few times just to keep things a little simpler. So theorem states that suppose f of x is continuous on the closed interval from a to b, and let n be any number between f of a and f of b, where f of a and f of b are not equal, then there exists a number c that's inside this open interval from a to b, such that f of c corresponds with n. Now, n between f of a and f of b, that means that f of a is less than n is less than f of b, or f of b is less than n, which is less than f of a. So it's some value of y somewhere in between the f of a and the f of b. All right, so we're going to use the intermediate value theorem to determine if f of c equal to 0.032 has a value c that exists on this interval. So first of all, and the function is x squared tan of x. All right, so first of all, we have to make sure that x squared tan of x is continuous on this interval. We know that tan has some restrictions. It's undefined at -pi/2 and pi/2 and every pi units from there. Those restrictions are outside of this domain, so that interval. So it is defined, the function is defined from 0 to pi/8. So we won't have any problems with continuity. So now I have to evaluate my function at these two endpoints of the interval. So f of 0, if you plug it in here, you get 0. And f of pi/8, well, you'll need a calculator for that. So it's about 0.638769. Make sure your calculator is in radian mode or you'll get a different answer. That's not correct. And since the n is this value, since it is between 0 and this 0.638769 value, then you can conclude that yes, there is a c that lives somewhere within 0 to pi/8, where f of c equals that y value of 0.032. All right, so let's take this a step further, where we're going to use the intermediate value theorem in order to help us find the roots of a function. And a root, also called the zeros, are basically the x-intercepts. It's where the y value is 0. And sometimes we know that we could find x-intercepts very easily, but there are functions that it is very difficult to find because there are these irrational numbers that are difficult to solve for. So this intermediate value theorem, along with something called the bisection method, allows us to get a pretty good guess of what that root would be. So in order to use intermediate value theorem and the bisection method, well, first it has to satisfy the intermediate value theorem. It's got to be continuous. And then we're going to use this concept of bisection. So first, as I mentioned, it's got to be continuous on the interval. And then this part is really important. Your f of a and your f of b have to be opposite signs. One has to be positive, one has to be negative. It doesn't matter which is positive and which is negative. They just have to be different. And the reason why that's important is if you have an f of a, and here my f of a is positive, and in this picture, my f of b is negative. Well, the only way to get a continuous function from a positive value to a negative value is to intersect the x-axis. And where it intersects the x-axis, that is your root or your zero. And that's actually what you're trying to find. Okay, so once you determine that they're opposite signs, you know that a root will exist. So your first guess on what that root will be the average of the two endpoints. So we're going to call it a midpoint, a plus b and divided by 2. So suppose I were just kind of estimating where that would be on this graph. I would say that my m, and I'll call it m1, is about here somewhere. Okay, and we can see that is not anywhere close to what my root is, but it gives me a better guess of getting closer than where I was before. We knew before it was between A and B, so now I have a more precise guess because now I'm going to check what the sign is of f of m sub 1. So f of m sub 1, in this case, is positive. So since f of m sub 1 is positive and f of b is negative, I can then guess that my next guess is somewhere between m sub 1 and b. So the next guess would be the sum of m sub 1 plus b divided by 2. So you keep taking that average. And again, I'm just going to guess where that is here just to illustrate what we're doing. So I would say m sub 2 is about here, and f of m sub 2 is down here, and that's negative. Since that's negative, when I guess what m sub 3 is, I need to guess that it is now between these two values, the one that was positive and the last one that was negative. So then I would average m sub 1 and m sub 2 to get a more precise guess. And again, if I were to guess, I would say it would be around here is m sub 3. So you can see that the more often I do this bisection, the closer you get to the actual root. So we're going to use this in this problem. So we want to find an interval of length 0.25 units within the interval from 1 to 2, which contains a root for this 7th degree polynomial, for this equation. All right, so the 0.25 is important because that's going to let me know when I should stop, because otherwise you could really keep doing this bisection method for quite a while. So when you're doing homework on this, pay attention to these directions so you know when to stop. So remember, first we have to determine that it is continuous. This is a polynomial function. All polynomial functions are continuous over all real numbers. So it is certainly continuous from 1 to 2. Then we need to check the values of f of 1 and f of 2. So one has to be negative, one has to be positive, and you're plugging it in here. Plug in f of 1, then plug in f of 2. I get these results. F of 1 is -6, f of 2 is 124. The numbers don't really matter, just the signs. So one is negative, one is positive. So we're good to move forward. That means that the function is going to cross the x-axis somewhere within this interval from 1 to 2. All right, so my first guess is the average. I'll call it m sub 1. The average of 1 and 2 is 1.5. So now I have to check the sign of 1.5. F of 1.5 gives me a value of 11.5859. That's a positive number. Remember, the last negative number was f of 1. So since f of 1.5 is positive and f of 1 is negative, then the root exists somewhere in between the two. So you take another average. I'll call it m sub 2. That gives me 1.25. 1.25 is a positive number. So again, you're always adding the x values where your function values were opposite in sign. So I have to check what my sign is at 1.25. F of 1.25 is -1.48. Okay, so that means that the last time I got a positive value was at 1.5. So that means that my root exists, or my zero exists, somewhere between 1.25 and 1.5. But the difference between these two numbers is 0.25 units, and that's exactly what the direction said. It said find a root within 0.25 units in length for this function. So you know that the root exists somewhere between 1.25 and 1.5. And if you were to graph it, you can use a graphing calculator or an app in order to show that. And if you were to graph this, you can see right here, there's a root right there, and it is right between 1.25 and 1.5, closer to the 1.25. So if we continued, we'd get more and more precise of an answer. Right, so that's it for that homework. For that lesson. You can try the homework. Good luck.